All right, so before we officially do anything, let me just remind you that if you want to correct any of your homework for these first several homeworks, that's due by Monday with your exam. You throw the things up here in the resubmission link. I graded your most recent homework yesterday, so you should have all that feedback in and a score in. So you just, if you want to correct something, just like in DEs or whatever, you redo it, clearly label it, throw it in this link, and I eventually get around to looking at it. So several of you have done that, and like I've just shifted scores from like a 50 out of 70 to a 70 out of 70, or whatever the scores are, if the work is correct now. So that's something you can do before Monday as part of studying for the exam if you would like. The other thing to say is that on your exam, the instructions will be the same as on this old one. In particular, I mentioned this on whatever the last day of class was on Wednesday. You can bring a sheet of notes in. So these are handwritten, or if you like, you can write them on your iPad and print them off. But anyway, you can bring notes in. So notice this old exam has no formulas on it. So you write those down, you explain what the letters mean to yourself on your sheet of paper, right? So for example, like, this is a coupon collector's problem. So you should have that formula written down and labeled and all that sort of thing. I don't know, is there something else? You can write down the optimal stopping theorem, that's what this problem is, and so on, right? Gambler's ruin, you should write that formula down. Anyway, so this sheet of paper that you write down stuff on, I'm not going to grade it, I'm not going to look at it. You can put whatever you want on there. So you could, I don't know, you could put all of these questions and their answers on there if you want. I don't know. I mean, put whatever you want on there. You have sample questions. You can have encouraging notes to yourself. I don't know. Just write down something. So this old exam is pretty representative of what you guys will see. I mean, it covers everything. I mean, are there any shocks on here? Question 1, first day of class, I said you'd have to do that on your first exam. I don't know if you can remember that back that far, right? But I'm going to give you a statement. Probability is this. And I'm just going to ask you to interpret what that means, right? Can you say in plain English what that means without referencing the word probability, right? This is standard chapter 2 material here. House percentage probably. Expected payout, sort of like house percentage. Coupon collector. It's just like the standard run of stuff. So anyway, what you'll see will be like this. Not exactly this with numbers changed or whatever, right? But this is representative. The problems from Wednesday, whose solutions were embarrassingly riddled with typos, which I think have been fixed now. But anyway, boy, this thing. These problems are also representative. I don't know what the hell I was doing when I was working through these myself and filling out these solutions. I think I eventually started getting them right around question 3. So that's encouraging, right? I think these solutions are now all correct. Okay, so today we're just going to do whatever you think is most helpful. I'm happy to discuss any of these problems. I'm happy to have you guys work on your own on some of these problems you haven't done yet. If you want to work through some of the old exam problems and get like sample grades on those, I can certainly do that. So let me just ask, what do people think would be most helpful? Okay, on the stuff from Wednesday or from the old exam? All right, let's at least walk through it and see if you guys, I'll just ask, right? If you want to discuss any of these. Question 1, if I give you a statement that involves no calculation but gives you a probability, can you explain what that means? Without using the word probability or chance or whatever, right? You have to fully explain what it means without self-reference. Everybody can? Does somebody want to throw out a sample answer? Or are we all just happy with what's in our heads right now? Yeah.
I wrote down if you roll 3 dice and take the sum 10 times, and each event be the sum of a sum of 4 from those 3 dice. The limit as n approaches infinity is h of n over n equals 3 over 200.
That's very good, right? So if we weren't socially distanced, Joseph would high five him right now, right? So Trevor gave the formal definition, right, involving the limit. You don't have to do that, but that is the formal way of saying it, right? You could also say something like this, right? If I roll these 3 dice over and over and over again, right? You know, so you have to say something about going out to infinity, right? Over and over again. Then in the long run or whatever, right, the proportion of rolls whose sum is 4 approaches 3 over 216, or limits to 3 over 216, or goes to 3 over, or however you want to say it, right? So if you don't like the full rigor of the limit, you don't have to use a limit, but you do have to somehow like Englishitize the idea of that limit there. Right, this is a proportion, right? So proportion of what? Proportion of times you get a sum of 4 out of however many rolls. Y'all feel like you can do that? So again, if you can't explain what a probability means, I'm not sure what we're doing here, right? So a question like this will certainly appear on your exam. Okay, here's another, this one's more open-ended, I guess, right? What's the deal with expected value? Why do we care about that? Why are we doing that over and over again? There's, of course, no one right answer here, but I don't know. You guys agree that's a useful concept? Or do you think it's just a silly go away or something, right? What would somebody write here?
To understand the profit in the long run.
Sure. So it's how you can understand why a casino makes money, right? That's basically what Jacob is saying. That's an answer, right? And I think that's what most of the students wrote, whatever spring this was, right? You know, other answers are like in games where money is involved, right? The win probability by itself doesn't really tell you anything, right? The expected payout or expected profit or whatever Jacob said, right? That tells you whether you should play a game or not, whether you make money in the long run. Things like this. You can say anything like that. That's fine. Okay, so those are sort of like squishy questions, I guess, right? Here's a non-squishy question. This is a callback to chapter 2. So we did a couple questions like this in chapter 2 in class and homework. You guys remember how to do this sort of thing? Yeah, okay. Let me take Trenton's answer. So at the very least, we got to set up a fraction, you know. We got to do 2 counts, right? The bottom's complete freedom, just what can happen with 40 rolls, is that right? So let me just slot in what Trenton said. That goes up here. I'm sorry, what did you say, Trenton? 42 is 5? Okay, where the 42 is 5 come from? Yeah, from the 40 rolls, you got to select the 5 that hit for you, right? Do I agree with that? So once you choose those 5 slots, how many choices do you have for what goes in those 5 slots? How much freedom do you have there? No freedom, right? Okay, but then the other 35 slots, right? How much freedom you got there? A lot of freedom, except you can't do another, I can't see anything with a glare. No 2, right? Do we agree with that? So you have almost complete freedom, but 5 options in this 35 slot, right? So we did questions like this with dice rolling in chapter 2, with coin flipping. With coin flipping, this was missing actually. Y'all remember this? Although it wasn't missing, it was just 1 to the 3/5, right? Because once you slot in the heads, there's no option for where the tails go, right? This is a 2 option thing, right? And then what goes down here? What's just the total count? Yeah. 6 options in general, 40 times. So there's your complete freedom. You guys remember doing things like this? So that's what it wants from you. So the most common error here actually on this exam was this. Right? And you can see why people make that error, because if you've answered this question most in respect to coin flipping, right? You don't need the term here, right? But if you have more freedom than just tails, you got to throw that term in. Okay. So far we're doing pretty good, right? I ask you if you can do this, and all of you nod, right? That's a good sign. Okay. So this is a classic use of N choose K, so you'll certainly see something like that. Yeah, okay, with games on an exam, we can't get too cute, can we, right? Because you only got an hour and 10 minutes at most. So I can't be asking you some sort of like advanced variant of Chuck-a-Luck or whatever, right? You got to keep things kind of streamlined here. So this game here I made up for this exam. You can't play this anywhere, but it's very small, right? So what, you roll 3 standard dice. 6s are what you want, apparently, in this game I made up, right? You roll 3 6s, wow, 50 times what you bet. That's pretty good. If you get a match, but not a 6 match, you get 20 times what you bet. Otherwise, you lose. Okay. So, there's all sorts of things I could ask you. I could ask you what's the house percentage. I could ask you your win probability, your loss probability, whatever, right? Expected payout. So there are more questions here that I could have asked, but I decided to go with your loss probability and expected payout with an interpretation. So can you guys do this one? Yeah. So the students who did this successfully took different tacks. Like there's not one way you could solve this, but let's just do what you're describing. So we need a payout, expected payout anyway sometime, right? So here are the 3 outcomes. So the casino is going to hand you back 50 times what you bet, or it's going to hand you back 20 times what you bet, or it's going to hand you back nothing. And so one of the most common errors in the homework, right, is confusing payout with profit. You have to be consistent, right? These are payout numbers. Like you've already paid to play, right? And the casino is going to hand this back to you if you win big, this back to you if you win second big, or they'll hand you back nothing to keep your money. So this problem, part B, asks for payout. So those are payout numbers. Okay, so again, some of you might be tempted to write like a negative M right there, right? That's not a payout. The casino's not paying you negative M dollars at the last stage. If you want to put a negative M there, then I guess this would be like a 19M profit, right? This would be like a 49M or something. Did I say that right? I said that right. Okay, yeah, anyway. So these are payout numbers. Okay, so now we can fill in the chart. And as always, right, if you're going to fill in a chart like this, there are three probabilities to fill in. You should ask yourself, what's the hardest one? And then avoid that, right? I agree with that. Okay, which of these can we do the easiest? Okay, this one is probably the easiest because it's really hard to win, right? So in terms of counting, there's probably not a lot to count. So they set up a fraction. How many ways can we win the big prize? Only one way, right? 3 6s. And not, right, it doesn't say match, right? Literally must be 3 6s. If it said 3 of a kind, like the one from the practice, I'd put a 6 up here. But only one way to win the grand prize. And then how many total ways for the game to go? 6 to the third, right? Agree with that? Okay, of these 2 things, what's the easiest one to calculate? Probably this one. Because, again, there's not so many ways you can win that 20M, right? So denominator is the same. How many ways can you win the 20M? Yeah, 5 ways, right? Pedro says, right? You have to get 3 of a kind. There's only 6 ways to do that, right? But you can't get the big winners, 3 of a kind. Okay, so then this guy here, the thing we actually cared about, right? The loss probability, we get for free by just doing 1 minus. So most of the students, I think, did it this way, right? They were like, I don't want to do that directly. I can do this, and then get for free what I want. I mean, some students did, they just jump right to this. You can do it that way, but especially given what you do at B, you may as well just do this. Is it okay with that? Okay, expected payout. How do we do that? Yeah. Down, hat, right? Okay, so again, that's why it's nice to have a 0 as an outcome, right? That's why your book does payout. Because you get zeros. Yeah.
So it seems on letter A, because that's for the probability, can we just leave the answer like it is right now?
You'd have to circle this or something, but yeah, just indicate. Yeah, that part A just wants that number. And then on B, expected payout is what? 50 m over 6 cubed plus 20 m times 5 over 6 cubed. If we want to make anything meaningful from that, we should simplify that. Because as you stare at it, it's like, I don't know, what is that? So on your exam, right, you have Wolfram, which can simplify things for you. If all part B1 was expected payout, you can just write that, right? You'd be done. So if you're going to interpret it, it's kind of hard to interpret when it's not simplified. So I'm just going to ask Wolfram to simmer that thing down for me. So simplify 50, oops, not simplify, simplify 50 times m over 6 to the third, 20 times m times 5, also over 6 to the third. I mean, obviously you don't have to use Wolfram for a little thing like this, but I don't know. 25m over 36, it says. 25m over 36 is a much nicer thing to try to interpret if you have to interpret. Okay. So if you want to now make sense of this, what is this communicating to you, right? Somebody explain what that is. What's that telling you? Yeah, sure. So in the long run, right? For every M dollars you bet, the casino pays you back 25/36 of that M dollars, right? That's right. Do you agree with that? So if you're the casino, you want people playing this game? Yeah, you do. Right? So that 50M, I mean, listen, oh, I got to pay out that much, but I mean, not really, not very often, right? 20M, that's a big payout, but not very often. So the expected payout tells you, like, you know, like tells you if these are well calibrated or not. And for an actual casino game, actually, these values actually aren't that well calibrated. This is actually too much of a casino's favor problem, you know? Casinos like things that are sort of closer to the tipping point, because I think it'll get people to play more often, right? Like if this were, say, 1 over 36M or something, right? Casinos like, yeah, I love that. For every dollar, I only give them back 1/36 of it, right? But then people won't play, right? Okay. So, you know, you certainly see something like this for a smallish game, right? So not sick bow or something, right, where it's sort of more subtle. So something where these probabilities are fairly approachable in the exam time frame. Can you guys do this? Can you slot this and then go to your sheet of notes and solve it pretty quickly? What's this? Coupon collector, right? So as soon as you slot it, you're like, ah, I got coupon collector formula somewhere in my notes, right? I can figure out how long it's going to take me to collect all 25 tokens, like how many boxes of cereal I have to buy, right? And if you do that, you get $2,100, right? Now, of course, each box of cereal costs this much, right? So you should figure out how much money you have to pay to get yourself this trip, right? So there's a little extra step here. You guys want to do that extra step, or are you happy that you could do that? Yeah. So we need the coupon collector formula, which is like, well, okay, first of all, we have to say what N is, right? What's N in this problem? 25, right? You got to know the number of tokens. Then that formula is something like this. Can somebody please confirm this? It's natural log, like 25 natural log 25, plus something like this. Okay, something like this. Is that right? Okay. So that's how many boxes of cereal you'll have to buy on average to collect all 25, right? Do they agree with that? Oh, sorry, Ben. Sorry, Ben. So we just, we're doing this number 5 and I slotted that 25 into the coupon collector formula. Okay, so if it takes you 95 boxes of cereal to win, how do you decide if you should try to do this thing or not?
The 95 boxes times the 4, whatever is less
Yeah.
than $2,100, I guess.
Yeah, so on average, it'll cost you $405 to win this prize. Okay,
It's like a one-time only kind of game, but I just buy like, you just keep buying 95 boxes.
yeah, it's assumed that like you
Only win.
you just sort of win, yeah. You collect all the tokens, then you're done. But if this is literally how they set this up, then yeah, you should go. If you've seen Punch Drunk Love, you ever see that? The guy's just like buying pudding cups over and over again, right? You should go full Punch Drunk Love on this problem. Anyway, somebody's getting fired, aren't they? Right? You agree? Captain Crunch is going to fire his first mate or something, right? Anyway, if Captain Crunch wants to run a promotion like this, what they really should do is not have it be a classical coupon collector problem where all tokens are equally likely, right? They should have like a couple of tokens that are super hard to get or something, right?
Well, if you're trying to get rid of inventory, like, no one's gonna buy 95 boxes each year.
That's true. It should still be better calibrated than this, though, right? Like $405 is nowhere near this 2,100. So probably still somebody's getting fired. But yeah, that's a good point, right? If you just want to clear out a bunch of inventory, you can do this sort of short term, like on average, sort of payout when you take in. Okay. All right. So you're sort of like a classic lottery problem. We've had this in homework, had this in class. Now, some of you have pointed out that these kinds of questions are difficult, right? You pointed out because they are. But it is worth, again, pointing out that you can have a sheet of notes. So if you want to just have your homework problem on that sheet of notes or something, right, to remind yourself what the logic is, that's fine. Okay. So let's just walk through these. So again, we don't have to do these if you don't want to, but we can just take a poll, see if you want to see solutions here.
Yeah, we could.
Yeah, right, poll taken. No, you can just go through them. Order doesn't matter, right? So you're just choosing 5 numbers all different between 1 and 30, right? And you just want to choose the correct 5 numbers. Doesn't matter what order you said the numbers out loud. So if you buy 2 different tickets today, what's the probability you win this lottery? How do you answer something like that? You could, but if you do that, that actually assumes the order matters. Yeah. Yeah, so this lottery, there are 30 choose 5 ways for it to go, right? Sorry, let me just clear this up. So if you're going to build a fraction here, here's everything that could happen. And again, Pedro, what you were saying was sort of correct. It's just if it said order matters, then you do like your 30 times 20 times 28. So here's complete freedom, right? How many ways do you win? 2, right? You got 2 tickets. I don't know. It's not super likely, right? Probably. Now, I should say, one homework problem I wanted to assign, but I couldn't dig up the article. But somebody here mentioned it one time. There was this lottery in Australia or someplace where they butchered the payout structure. They made it so that the payout was way too big for like the 3rd and 4th place prizes. Okay, the big prizes are always big, right? But for like the 3rd and 4th place prizes, they made the prizes too big so that it actually became profitable for you to buy every single ticket. So that's what somebody did. Somebody noticed that, and they bought every single ticket. They won a lot of money off of doing that. Anyway, but I couldn't find the article where I read that, so I didn't assign it. But anyway, I was reminded of that story because this is about a lottery. So you can follow what I'm saying, right? Oh yeah, I should check on Ben, make sure you can see the board. Okay, so anyway, part A, I just want to see this fraction set up. You got a calculator, right? Ask Wolfram what that is. So there's no like complement there, there's no birthday problem, whatever, right? But now part B is more subtle, right? The lottery wants 2,000 times. What's the probability that like sometime you see the same numbers, right? So like on Tuesday of this week and then maybe Thursday of some week way down the line, you get a number match, right? So what would that look like? Like, so maybe today the numbers are like this. And then maybe 3 weeks from now, the numbers are also like that, right? What's the probability you get a match like that? Okay, so what kind of problem is this? How would you set this up? How do you approach it? Yeah, this is a birthday problem. So you have the 2,000 runs are like 2,000 separate people. Each run of the lottery is being assigned a number analogous to a birthday, right? So with you guys, if I lined you all up and I would give you a number between 1 and 365, right? This is like lining the lotteries up and not between 1 and 365, but how many birthdays are there here? Like there aren't 365 numbers to assign the first lottery, right? Yeah, a lot of birthdays, right? Possible for this lottery, right? So here, people, and we have things similar to this in the homework, right? And in class, the people are like lotto run. Or, you know, again, like each run, it's like a compartment, right? Remember that homework question was like, just generally speaking, birthday problems are like you got a bunch of compartments or boxes, and you're gonna like be dropping balls in there, right? Things like that. You can think of that story also if you want. And birthdays are the lotto outcomes. There are a lot of outcomes. So you don't have to conceptualize the problem that way, but if you do, then you're like, oh, lotto runs. I don't know how many of those there are, right? I mean, Tom says 4,000 or something, let's say 2,000. I know how many possible outcomes there are because the problem says 32.5 basically. I mean, it's been handed to you, but you import that from part A. And so then once you make that realization, hopefully on your sheet of notes, you have a little formula or something, right, for that. You just plug that N and K into the formula. Right, this is N, this is K. So that's what most of the students on this exam did for that 6B. Questions or comments on that? Now, some students didn't do this. Some students went like this. They said, well, I need to think about never having a match ever, right? Any drawing on any day can't match any drawing on any other day. So they said, okay, well, on day 1, I have 30 choose 5 options for my lottery in general. So on any given day, here are the number of options you have if you have freedom, right? Up top, though, you have this constraint of no matches, right? If you're going to have no matches, day 1, you can do whatever you want, but then on day 2, you can't match with day 1. And on day 3, you can't match with either of the first 2 days. And so on down the line, right? They set up the complementary fraction we had for the birthday problem. They got it that way, you know. That's fine, you can do that. Just takes a little longer. You guys see what I'm saying? Like they just rediscovered the birthday logic, right? And plug into the formula. But, I mean, you can do that if you want. Okay, so anyway, so 6B is a birthday problem. Okay, so C, what's the probability 5 numbers are chosen twice in a row? That's pretty limited, right? Seems unlikely. Same 5 numbers 2 days in a row. How do you answer a question like that?
The first day would be 30 choose 5 over any second day there's only 1.
Yeah, so you use basically, many of you guys did this in the homework, right? So there are 2 days, right? On the first day, you have complete freedom in the denominator like always, right? But you also have complete freedom in the top, right? The anything. But then a string says on the second day, we still have complete freedom in the denominator, but we have to match the first day. So there's the probability of winning, of matching 2 days in a row. And again, if I were like, oh, not just match, but like, what's the probability that 2 days in a row. What's the probability of 2 days in a row? That was the outcome on both days, right? Specific outcome, right? So not just a match, but that exact match. What happens in this fraction? What changes? 1 right here, right? You don't have complete freedom on either day, do you, right? So again, it depends on how the question's asked. This was the mistake those officials made in that homework question. So anyway, so again, part C is not really any complement or whatever, right? But then part D, I suppose there is a complement here, right? Okay, so now there's like 100 lotteries total. What's the probability at least one of them choose the same number 5 days in a row, right? And again, we're not thinking about 2,000 runs, just today, right? Yeah, today and tomorrow, right? So the probability a given lottery gets a hit like that is like this, right? So here's the probability the lottery that we're looking at right now gets 2 days in a row, right? It gets a match. But now we have a bunch of lotteries running, right? So presumably, if I broaden my scope, right, and I ask, well, just what's the probability of this kind of thing happens somewhere? Surely the probability goes up, right? I agree with that. And again, we had problems like this in the homework. So there are multiple ways to approach this. I don't know, somebody want to throw out one of the approaches they would take to something like this? I'm sorry, I just couldn't quite hear you. You're fine. I'm not saying what you said was wrong, I just couldn't hear. Oh, okay. It's fine if it's wrong. So the reason this is here is like part B is a complementary problem, but you can plug into the birthday form if you want to, right? Part D, though, you actually really have to grapple with the complement because it's not really a birthday problem. So one way you could phrase this is like, what's the probability that this thing happens nowhere, right? Because saying it happens at least one place, there's a lot of freedom, right? It could happen here, 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 or all three at once, or whatever, right? You know. So you could just think about, well, what's the probability that they all miss, right? So the probability of a single miss is this. I agree with that? It's probably you don't get 2 in a row. It's pretty high probability, right? So here's don't get 2 in a row for a single lottery, right? Now, do you guys remember what happens if you want to take the 100 lotteries into account? Remember what happens to this? If you want to miss now, not just here, but also here, also here, also here, also here. Remember what happens to this? Okay, you can just grab the logic we did from class to say, oh, that just repeats its way down the line, right? At this point, you can use a chance tree to see that if you want to, right? But I got to miss here, and I got to miss here. That creates a multiplication. And I got to miss here, and here. So another one, right? So this is the probability miss everywhere. So then you got to just see what that is and see what the opposite of that is. So let me just go to Wolfram. Okay, so again, I'm just showing on the board the punchline, right? So this wasn't so easy to get at the time, but this was the punchline. And you can grab the punchline if you want to, right? You're not trying to reinvent everything on an exam. Or are you? I don't know. Okay, so 1 minus 1 divided by 30, choose 5. Okay, that's really high, right? Right, the probability you don't get 2 in a row is real high. That shouldn't surprise us, right? But now we got to not get 2 in a row in a bunch of separate lotteries, right? Now all 100 have to miss. Now, of course, this is still really high, right? Everybody see that? It's still 0.99, but it's not as high, right? All right, what was this? It was 0.99, 99999 or something, right? So now if you do it 100 lotteries, you've knocked it down some, still 0.999. So here's the probability that all 100 lotteries don't do this thing, right? So then the probability you get a hit somewhere is just the opposite of that. So I wouldn't recommend maybe typing all this into 1 so that you can. It looks weird to have 1 minus 1 minus, right? But there you go. The probability of getting a hit somewhere is not minuscule, right? It's not like times 10 to the negative 20th or something. There's a 0.07% chance. And of course, if there, if there's like 10,000 lotteries or it's the same lottery running 10,000 times, you can just keep, there's 100,000 lotteries, right? 100,000 lotteries, now you get a coin flip chance of this happening sometime, right? Everybody see that? So the more you let a system run, or the more data you have, or whatever, right? The likelier it is that some kind of crazy thing happens somewhere, right? But with only 100 lotteries, we don't see that kind of extreme. Anyway, this was the question that most students missed on this whole exam, and honestly, I think it's because they didn't. They recognized they had trouble with it in their homework, but then didn't bother to put it on their sheet of notes. I didn't see anything like this in anybody's sheet of notes. And I was curious why. I don't know. They got cocky, maybe. I don't know. So anyway, this is the hardest one. If you can't get this one, I mean, that's to be expected, I guess. The students overall still did really well on this. The average was like an 83, 84, something like that. That's pretty good, if I remember correctly. Okay, so sorry, before we move on, number 6, this definitely was the hardest page of the exam. Any concerns? Any potential stumbling blocks? All right, number 7, really the only issue is the way students phrase things sometimes, because if you're not careful about the way you phrase an answer here, you can say something that's like, if I read it literally, even though I know what you're trying to say, if I read it literally, it's like extremely wrong. Okay, you gotta be a little careful how you phrase things here. So none of the students who took this exam had any trouble recognizing this as optimal stopping, right? So like, hey, optimal stopping, I got that on my sheet of notes, N over E, I go there, right? They just had trouble articulating what the actual strategy was. And this came up in the homework here. So let's that you guys just gave me on Wednesday. So let's articulate a strategy. This is a fairly contrived situation here, right? Okay. What is the strategy to make sure you arrest the head mobster? Is that what I'm asking? Who happens to be the tallest? Wow. Man, I was really reaching here for a problem. Anyway, articulate a strategy. How would you answer this question? It's roughly 13, right?
Let the first 13 lobsters walk out, write down their heights. The next monster walks out as tall as the first 13.
Okay, so what Trenton said would receive full credit. Let me take what he said and mangle it slightly. I'll see what you think. So I don't remember exactly how you phrase it, Trenton, but that's my memory. I'll write it down. So you let first 13 monsters go. You're not going to arrest them. Use them. Basically, what Trenton was saying, right, was to establish a baseline. So Trenton said, like, well, you write down all their heights, right? So of these 13 mobsters, one of them was the tallest, right? So basically just record that, right? So from the first 13, you got your baseline, right? And then I'm gonna write down what Trenton didn't say. But this came up in the homework on maybe like a third of the homework, something like that. So then arrest 14th mobster. So this is what the students who got it wrong last time, they made sort of a mistake like this. What about this?
Supposed to be the next one that goes up, like above the baseline, not necessarily the exact next one.
Yeah, there's no guarantee that this one will like surpass this baseline to establish, right? The 14th mobster could be super short in this context, right? And you wouldn't want to be like, oh, just because he's the 14th, I'll arrest him, right? So I'm now going to make the change that Julia said and what Trent said, right? So now you arrest the next mobster that comes along who surpasses that baseline, however you want to say it, something like this. So that next mobster that comes along that's taller than this baseline might be mobster 22 or something. I don't know. Might be mobster 28. Well, there is no 28. Oh, yeah, there is 28. And now, of course, it's possible, right? It's possible that the tallest mobster was in these first 13.
Yeah, what if the first
Whoops.
one 7 foot?
Yeah, right?
3 inches tall?
Yeah. So this is about maximizing your probability. It's not guaranteeing anything for us, right? So now what I don't take off points for in problems like this, but you really should say, but I don't take points off. In the homework, nobody said it. I didn't take any points off. But you should sort of say, what happens if you never surpass that baseline, right? Again, what if, whoops, one of the first 13 was the tallest? What happens then? Not a bad answer, yeah. You actually have to arrest the last one, right? So again, the standard story for this is like marriage partners, right? You're going to get married, you've decided, right? Nobody wants to die alone, do they? I don't know. After you're married for a while. You revise your attitudes on things like that. Anyway, you decided you're going to get married, right? So what that means is that if you reach the end of the line and whoops, you let the soulmate go in the first 13, you're going to propose marriage to the last person in the line. Anyway, so I didn't take off points, but it is worth pointing out. The strategy is a complete strategy, right? It tells you what to do no matter what. So you may end up arresting that 35th mobster who maybe is super short, but again, there's no guarantees with a probability like this. The question that's missing from this that I could ask you is not only what is the strategy, but I could ask you, what is the probability the strategy works out for you, right? What is the probability you arrest the person that you wanted to arrest, What's that probability? Now, if this were an exam, right, and I ask you that, your answer should be, I don't know off the top of my head, but no. Whatever what, sorry? No. Yeah, so if this were an exam, you wouldn't be doing what you just did right now, right? Because you guys were saying sort of natural answers, but they're still sort of guesses, right? So if this is an exam, instead of guessing, what do you do? Well, I guess you could say that. Be honest, right? Hopefully, what you do is something like this. Wow, sure as handy, I got this sheet of notes right here where I wrote things down, right? So I don't know right this second, but I'm going to check the sheet of notes, right? Because the theorem for optimal stopping gave you this N over E. It also gave you the probability that the strategy works out, right? 1 over E. Yeah, isn't that nice? Yeah, it was something like 37%. Whoa. Class is over, I guess, right? I thought class went till 12:20, but I don't know. Maybe not today. It's finally warm enough to be outside, so maybe we'll. So anyway, again, like you don't want to like memorize this, but you do want to like if there's a theorem, you want to write down all the pieces of it, right? So again, right, this is not even a coin flip chance of working out for you, right? So there's no guarantee that it's going to work out, but it's about maximizing your probability of this kind of strategy working, right? 37% is about as good as you can get, given your limited amount of information and stuff, right? So again, like not to overstate or beat a dead horse or something here, right? But like on any of these problems, if you're like, man, I don't know how to do this, the correct response is to go to your sheet of notes, which hopefully was well constructed, right? I mean, any strategy I suppose could work out.
What's the probability of that?
I mean, probably 0, but as we discussed before, 0 actually doesn't in some global sense doesn't always mean impossible, in some sort of philosophical sense. So I don't know, try. Maybe we don't need to do this one, but do you guys recognize this? What do you do for this? Yeah, optimal, I mean, not optimal, gambler's ruin, right? So hopefully you have that formula written down with an explanation of what all the letters mean, right? But then you can just grab that formula, slot in the numbers, and then you do part A. Now in part A, you were betting $200 per spin, and you showed up with $1,000, right? How much should you be betting per spin in order to maximize your probability of reaching this target you have here? Why 200? Oh, I'm sorry. Yeah, yes, you're right, Jacob. Sorry. 20 is what you bet per spin on A, right? I didn't read my own question. That's something you should do, right? You should read the question. Yeah. The table max is 200, yes, right? So you bet the table max because of what Shane said, right? Shane's logic still holds here. If the game is tilted against you, you want to expose your bankroll to as little time as possible. So yeah, so the answer to part B is 200 because, and fill in some of that logic. None of the students really had any problems with this that I remember. Oh, no, there actually was a cell here that a few people missed. Yeah, so let's talk about this one real quick. Yeah.
So the answer for part B would be 200 and I'll run.
200, yeah, because this game is tilted against you. So the shorter you can make the game, the less you're going to let that long run kick in, right?
So it's not in the long run, just 200.
You're trying to make the game not in the long run, yeah. So you're still going to lose a lot if you bet your max, and when you lose, you're going to lose more quickly. But it's better for you to shorten the time of the game so the long run can't kick in on you. Yeah, so you say something like that. Yeah, okay. Shuffle, record, okay. Oh, sorry, Ben. Okay, so you shuffle a standard 52-card deck, record the card you see, put that card back in the deck and reshuffle. Continue until you've seen all 52 possible cards, right? Now notice, it's not asking you to solve, right? Actually, what I remember most about this question was students calling me over and asking, do I have to solve this? I say no. Just, is it a coupon collector's problem or not? And if not, explain why not. Or if it is, explain why it is, right? You don't have to solve it. So anyway, this is certainly coupon collector-like. Is it a literal coupon collector's problem or not? What do you guys think?
I mean, yeah, because they all.
Yeah, right. So what if I took this out? Right, that's sort of a key phrase, isn't it? No longer, right? Everybody see that? Because as the process moves, things get more likely, right? If you haven't seen the Ace of Hearts yet, you probably have seeing it later is higher, right? Because there's fewer cards left. Yeah, this is a coupon collector's problem. So the students who got this right, most of them got it right. They said what you guys just said. You're collecting the cards, and each card has equal probability of showing up because you're putting it back in the deck and reshuffling. So, 10 is kind of a soft question. Let's come back to it in a second. Oh, we're at the end, right? Okay, so 11. Yeah, okay, so on this particular exam, 6D was the question that was the most difficult for the students in terms of who got it right, number of people got it right, and then 11 was the second hardest one. So the students who corrected their homework on the craps homework got this one right, I guess I should say. So this, of course, is not a craps problem, but do you recognize this as that same sort of milieu or something? It's in the extended craps universe, right? What do you guys think about this? Yeah, let's do that. Stop sharing. let's make sure we all process the question. So she has a 90% chance of landing her ball in play. So there's a 10% chance that she serves the ball out of bounds and you just win outright. That's what that's saying, right? So there's a 10% chance that you just win straight up. That's similar to in craps, right? Where there's a 6 out of 36 chance you just win straight up. You roll 7. But if she lands the ball in play, then now the process kicks off. So you can draw a tree or not. Let me just first start gathering data here. And sorry, Ben, make sure you can. There we go. And that glare, it's an obnoxious thing. Oh, I made it worse. That's a little better. Okay. Okay, so the probability you win, there's a 10% chance you just win straight up, right? She served the ball out of bounds.
But then she has a second serve.
Yeah, so I assume nobody here is a tennis player. Is gonna yell at me like that. Yeah, so let's say this is a 10% chance she does a double fault, I guess, right? Yeah. Yeah, when I taught this last time, I think Hannah Wayne yelled at me for butchering the rules of tennis. Yeah. Oh yeah, it says assume she has only one serve. Yeah. So there I was asking Hannah Wayne not to yell at me, and then she did anyway. But whatever. Okay, so it's a 10% chance you win. Otherwise, this process kicks off, right? So she serves the ball to you now. Now it's in play, right? So now you hit back. On any given hit, you have a 20% chance of winning the point, right? So here, this is she serves out of bounds. So like the point doesn't really even start. Okay, or she lands it inbounds, right? So here, just a win straight up. Or she serves inbounds. What's the probability the ball lands inbounds when she serves? 0.9, okay? And then you smash it back at her, right? It's like a crappy serve. You just slam it right back. And you win, right? So what's the probability you just win here? 0.2? Do we see that?
Would it not have go to like the chance of her winning then? What if you don't hit the ball? So would it not go 0.2, like you lose 26% of the time? You hit the ball to you, and it's a good serve, or if you miss it, choose the point.
Yeah, right, so that's all kind of embedded right here, right? So there's a 20% chance you just win outright, but you also, I suppose, just lose outright, or lose some way this way, right? We don't have to worry about losses, because all we care about is probably we win.
Bro.
Yeah, it's not saying that
I don't, yeah, I
she that lanes and
Bro,
it's not saying that you miss it. It's either if it's inbounds, you return it. If not, then you know, like you said, losing it.
So, I mean, sorry, Trevor, is this okay? So it's also possible, right? So it's possible you just squirt the ball out of bounds so you lose, or you just return it to her, right? But either one of those doesn't really matter. You just don't terminate here to win. All you care about is where do I terminate and win, It's like you could slam it back at her, but then she hits it back to you and you haven't immediately won, You're shaking your head at me.
I'll talk to you about it later.
Okay. So anyway, this is like you win on your first hit, right? So for you to win on your first hit, she has to land in a bounce to you, then you have to hit it back to her really good. Whatever, right? Is that good tennis language? That's what you should do. When somebody serves it to you, hit them back to them real good so that you win. Or you hope they double fault, I guess. So anyways, now you got this going. Okay. It could also, though, land in bounds. You then don't win on your hit, right? You don't win on your hit would mean like a 0.8. Don't win. She then doesn't win on her hit, so like somehow makes it back to you, right? So probably she wins as 0.26. She can't win. She's got to get it back to you. And then you then you then finally win here. So it has the exact same flavor as the dart throwing question from the homework, right? Basically, the only difference between this and the dart throwing question is you have this additional 0.1 out front to deal with the serve thing, right? So here's an immediate win. Here's a win on your first hit, 0.9, 0.2. Here's a win on your second hit. She has to land in a bounds. Then you don't win. She doesn't win, but they know you win, right? And if you keep this chain going, right, you can just keep expanding this out. So what would this look like? Like a little loop here. So you just have to have this sort of ping-ponging back and forth, right? Ping-ponging being the real tennis, right, Pedro? This. Right? You don't win, she doesn't win, you don't win, she doesn't win, but then finally, at the end, you smash it and you win. And that's preceded by her actually managing to land it in bounds, right? So this whole sort of branch can just keep getting bigger and bigger and bigger. So the students who made errors here, I mean, this is a pretty subtle question, right? Again, if you fully process that dart throwing question, it's not as bad, but some students didn't fully process that question. The most common error were things like leaving off this 0.9, just forgetting she has to land it in bounds first, things like that. That didn't lose those students very many points. But in the end, you get something like this. You get your win probability is the 10% you just win up front plus this thing, right? Which can go on potentially forever. Right? Just keep backward, backward, backward. Or finally you win at the end. So this you would just hand off to Wolfram. But that's the idea, right? You win up front, or you don't just win up front. She lands it in bounds. And now you don't win, she doesn't win. You don't win, she doesn't win, right? Backward, backward. Just like with the darts, right? You miss, partner miss, you miss, partner miss. Until finally at the end, you finally get your hit. Let's just see what that is. Okay, so what is it? 0.98 to the I, 6 to the I, and then you smash at the end. What? Assuming I is the, why would it do that? It's saying it's thinking of I as square root of -1. Okay. I mean, I told you here it wasn't, right? Why is it behaving like this? All right. Take this off.
It's like
Oh,
not
did
getting
I?
the stem part.
Maybe I forgot the syntax. If I do that, I thought I could type it either way. Yeah, it is like forgetting what the word sum means. Why is it doing that? I mean,
Try from K equals 0 to
of. Hang on. Sometimes it's very picky about multiplication symbols, and I never know why. Doesn't matter.
Well, if anything's wrong, look at that.
Oh, okay. Yes. That red misspelling error, right? Should have told me something. Interpreting infinity as infinity. All right, that's a good idea. Did I still spell it wrong? I did still spell it wrong. Oh, all right, well, whatever. Now it finally knows what I'm talking about. Sorry. Okay, so this, I took off the 0.1 plus, right? Because I was confused. So your win probability is 56% or so, right? So basically, even though your partner's better than you, there's a 10% chance you just win straight up, right? Because they don't, like if they always serve the ball in bounds, then I guess this probability would shift down quite a bit, right? Because if they always serve the ball in bounds, never double faulted or whatever, then this disappears. Now let's see. Oh, you still have a 51% chance of winning. Huh. Wonder why that is. Well, anyway, that 55% was the correct answer on this one. All right, so again, anyway, the reason this question existed was it's like that dart throwing, right? Back, forth, back, forth. You get an infinite series with the two separate, like, non-terminating probabilities there, right? So you could see a literal craps problem, or you could see something like the dart throwing thing, right? Which isn't literally craps, but the same idea. All right, so anyway, so we made it through this whole exam. I guess that's good. I guess it's good we could do that together in an hour.
You just do that on Monday.
I mean, I don't know. I'd prefer to sit back there and just not do anything. So,
Are you gonna take the exam on like iPad or just like?
no, I'm actually allowed to hand you paper for exams
You are, you
for
said?
some reason. Yeah,
Wow.
so I'm gonna do that. Yeah, it'll just be regular. I mean, obviously, if you're not comfortable with that, then you can take it on your iPad.
Have you done a grade?
Yeah, I didn't finish them.
Are they?
Pretty good. What I looked at so far. Yeah. All right, so if anything bothers you, right, make sure that before Monday you send me an email. You can always send me an email with problems you've done, anything like that.